Hello friends, welcome to the 8th lecture. In today's class, we will study about area. Now you all will be astonished to know that whether it's a physics class or mathematics class. No, we need some data about area. So I'll ask you, area is a vector quantity? Area is a vector quantity or a scalar quantity? So probably most of you will tell area is a scalar quantity. Okay. Why? What was the reason behind it? Because if I'll tell you this is a rectangle, this is a rectangle of side A, B, C, D. Suppose this is 3 units, this is 4 units. I'll ask you what the area of this rectangle. All of you will tell me 12. Okay, 12 units square. But in today's class I'll tell you it is not 12. It should be either the area will be 12 k cap or 12 k cap with a minus sign. Okay, either of these two will be correct, not this one. So in today's class I'll tell you that area has to be considered as a vector, not as a scalar. You have to consider this as a vector. How? Let me show you. Suppose I fix origin here, and this is my x-axis which will contain I cap, and this is my y-axis which will contain the j cap. Okay, so I'll tell you that what will be the area then. It will be 3 cross 4, right hand thumb rule. Extend all your fingers towards 3 and curl it towards 4. You see your thumb will be up the plane. That means it will be along k axis. But if you go from 4 into 3, from j to I, if you take right hand thumb rule, your thumb will point into the plane of the paper. So that's why it will be minus k or plus k. Clear? So one thing we will observe here, that this rectangle is an example of open surface. Okay, so for open surface the direction is always perpendicular to the area. Okay, so another open surface example, let us take another example of open surface is a disk. So this is a disk whose radius is r. Okay, so if I'll tell what will be the area of this disk, then it will be either pi r square j cap, or it can be minus pi r square j cap. Now the question comes, sir, is it both of them are correct? Yes, both of them are correct. But while doing any problem, you have to consider anyone. If you consider plus, that is also okay. If you take minus also, that is okay. But throughout the problem, maintain the same sign, either plus or negative. Okay, so what conclusion can we make? That for open surfaces, do you have some examples? Yes, we have open surfaces like your rectangle, then you have got your square, you have got your this disk, etc. So for these open surfaces, the area vector direction is always perpendicular to the surface. Okay, so this is very important. For open surface, the direction will be perpendicular to the surface. Okay, the way I have told you about open surface, do we have something called closed surface? Yes, we have something called closed surface. Now can I give some examples? Yes, we have some examples, like your sphere is a closed surface. Okay, cube is also a closed surface, like this. For closed surfaces, then what to do? Now I know that if I want to draw a sphere on this paper, then what I have to do? I have to represent a circle only. Suppose this is the circle. Okay, so for this circle, what should be the direction? Either this one should be like this is the correct one, or it should be like this, the area vector. It will be inward or outward. Which one will be correct? Inward drawn normal or outward drawn normal? You see, this will be wrong, not inward. It is always outward drawn normal. Okay, so for a closed surface, if I want to draw, then what I can do is I have to draw my n caps like this, n cap in these directions. This will be my n caps. Okay, followed. So outward drawn normal for closed surface. So what I can write down is, for closed surface, the area direction will be outward drawn normal. Okay, outward drawn normal. Suppose I consider a cube. So let me construct a cube, which many problems will come on cube also. Let me construct a cube. So for this face, the n cap will be in which direction? It will be in this direction. Okay, suppose I consider another face. Suppose this face is there. For this face, what will be the direction? The n cap will be in this direction. Okay, so for a closed surface, the area direction will be outward drawn normal. So after following this area vector properly, then we will jump over to another concept, which is called electric flux. It is called electric flux. Area is a vector quantity. Now we came to know this flux will represented by phi will be a scalar quantity. We'll see how it will be a scalar quantity. So the next concept is electric flux. Okay. Now what is electric flux basically? So your electric flux is the count of number of field lines crossing an area. Suppose we have an area like this and we have got field lines in this manner. So we have to count the number of field lines which will cross this area. Okay, so basically it is defined as the count of number of field lines crossing an area. Okay, now what does it represent basically? For that, what does electric field lines represent? Your electric field lines represent energy. Okay, and your electric flux, what does it represent? It represents energy flow. This is very, very important to understand. Your field lines are nothing but energy, whereas the flux represents energy flow. Okay, so in order to derive this formula for electric flux, I will give you an example. Let me take an area in this manner. Now its area vector n cap is along this direction, right? Now electric field lines are coming in this manner. Okay, so what will happen? Most of the field lines will cross through this area. So the energy flow or the flux will be maximum. Here. Now suppose I have the same area here. The n cap direction is like this and my electric field lines are coming from up. Do you think that any of the electric field lines are entering this area? If no electric field lines are entering this area, then what will be the flux or the energy flow? The energy flow will be minimum. Okay, it is quite obvious. Now if I want to tell you what is the suppose I want to find out the angle between E and n cap, which is represented by theta. So theta is how much here? 0 degree, whereas theta will be how much here? 90 degree. So my point of saying is that your flux depends on three things. The first quantity is the electric field lines. Okay, the second one, you have to talk about the area, you have to talk about your area vector, and third thing is what? Is the angle. Which angle? Angle between electric field and your area vector, which is theta. Okay, so flux basically depends on these three things, and we know that your flux will be proportional to electric field magnitude, proportional to area magnitude, as well as it is proportional to theta. So if I want to construct a formula, then what I can write? Phi will be equal to EA cos theta or sin theta. Looking into this example, you can make out clearly that it will be not sin theta, rather it should be cos theta. So EA cos theta. So then what will be flux? The cos theta means dot product or cross product? It should be dot product. E dot A, and we know that dot product gives a scalar quantity. So your flux is a scalar quantity. I hope it is clear. If it is a scalar quantity, then the flux can be positive, negative, and zero. Anything is possible. Then what about its unit? What is the unit of the flux? It is Newton meter square per coulomb. So in general, we can write flux phi is equals to integration over the closed surface E dot ds, or in some books you will find it will be written integration over the closed surface dA. Now one more important thing which must have come to your mind, what is this symbol telling you? It is nothing but it is the integration over a closed surface, so I hope what is flux, that must be clear to you. Okay, you must have be clear about electric flux. Now there are very complicated situations where we need to calculate electric flux, so which is very difficult for us to find out using which formula, using this formula. So to make our life simpler, to rescue us, a scientist came forward whose name was Gauss, and he gave us the Gauss law. So the next topic what we will study is your Gauss law. Okay. Now this Gauss law is very important for us to understand. I'll explain you by taking an example, then I'll tell you this mathematical equation, right? Suppose I have got charges like Q1 here, Q2 here, and minus Q3 here, and then I have minus Q5 here, and here I will have Q4. Such kind of charge configuration is given to me. And I have been given a closed surface of this manner. This is a closed surface. Now it is asking you, how can you find out what is the flux associated with the closed surface? Phi net with the closed surface will be how much? Gauss told it will be Q1 plus Q2, since Q3 is minus, so minus Q3 divided by epsilon naught. So this will be the answer. Then the question comes, what is the contribution of Q4 and Q5? They will not contribute to the flux associated with the closed surface, as these charges are outside the closed surface. Okay. So what is the mathematical formula for this Gauss law? Your phi net will be equal to the total charge enclosed by the closed surface divided by epsilon naught. And I have already told you what is epsilon naught in our previous lectures. This is also equal to integration E dot ds. So this is basically your mathematical expression for your Gauss law. Okay. Now after following Gauss law, you should understand one more imaginary thing which is very vital for us in order to solve problems related to flux, and that imaginary thing is called a Gaussian surface. It is a Gaussian surface. Okay. So what is this surface? Is it real? No, it is not real. It is an imaginary surface. Acha, what all properties this surface have? The first the property it has is the electric field on the surface. Everywhere on the surface the electric field is same. On the Gaussian surface the electric field is same. Then the third one is the flux coming out of the surface is along the normal to the surface at every point. So it will come out normally to the surface. Now the Gauss law, which the statement which I have given, let us prove it. So this comes as a 3-mark question also. Proof of Gauss law. Okay. So for that what I will do, that one of the charges plus Q is given to us. Okay. And then to find out this Gauss law, we have to draw a Gaussian surface, and the Gaussian surface here is a sphere. The Gaussian surface here will be a sphere. Okay, since I have told you the properties of the Gaussian surface, that it should be, the electric field lines must be coming out normally from the surface. Okay, they should come out normally from the surface. So this is the electric field direction. Okay, it is quite obvious because it is plus q, and the radius of this Gaussian surface is r vector. And here what I will do is, I will take a very small area. I will take a very small area on this surface, and this direction will be in which direction? The area direction, n cap direction, will be along the electric field, and your radius is also along this, so r cap will also be along this direction. Okay, so what is this? This is actually the Gaussian surface, the imaginary surface which I have chosen, and for us, for this problem, it is a sphere. Okay, so now let me prove it. Once you have understood the diagram, we can calculate the electric field. What will be the electric field here? K into Q divided by R square into R cap. R cap tells me the direction. Then what is this area vector? ds vector will be how much? The direction is n cap and the magnitude is ds. Okay, then how to calculate the flux? I have taken a very small area. So for this small area, what will be the small amount of flux? D phi E will be the flux. E stands for your electric flux. It will be equal to E vector dot ds vector. So E vector is how much? K q by r square, and here it is r cap dot product with n cap ds. Why? Because E dot product ds, that's why dot product. And what will be this? Kq by r square in ds, because your r cap dot n cap, these are the unit vectors, so it will be r cap mod n cap mod. And what is the angle? Both of them are in the same direction. You see, angle between n cap and r cap, it is 0 degree, so it is cos 0. So what will be its value? It will be 1. Okay, then once we have got the small amount of flux associated with the small area, what will be the total flux through the Gaussian surface? Phi will be how much? Integrate d phi. Similarly, we have to integrate this RHS also. K q by r square, they are constant, they will come out. Integration ds. So integration ds will be how much? K q by r square. Integration of ds will be 4 pi r square. Okay, r square gets cancelled out. K will be how much? K will be 1 by 4 pi epsilon naught q into 4 pi. So 4 pi gets cancelled out. So you have q by epsilon naught. So phi will be q by q by epsilon naught. So this is how you can prove the Gauss law. So another important problem associated with this is the proof of Coulomb's law from Gauss law. We have to derive this Coulomb's law from Gauss law. Okay, from Coulomb's law we have to derive Gauss law. So again, for this, what I will do is, I will take a charge plus q1, right? And again, I have to choose a Gaussian surface. So let the Gaussian surface be a sphere for this case. So it will be like this. So now, so what will be your electric field will be in which direction? It will be along this direction, and this is your electric field due to q1. So what I will do is, in this is a Gaussian surface we have chosen, and the Gaussian surface is a sphere for us. I will take another charge q2 on the surface of the Gaussian surface, charge q2, and here I will take a very small area here, and n cap will be along this direction, right? So I hope all of you understood the diagram. Now from the Gauss law, what we have is your integration E dot ds is equals to charge enclosed by epsilon naught. So what is the charge enclosed here? Q1 is the charge enclosed. E dot ds means E ds cos theta will be there because it's a dot product. Okay, will be equal to how much? Q1 by epsilon naught. Now cos theta will be how much? Theta is the angle between E and area. Both of them are in the same direction. Theta is equal to 0 degree. So cos 0 degree is equal to 1. So let me put it here. So I will have E integration E ds is equals to Q1 by epsilon naught. Now I have told you on the Gaussian surface the electric field is constant, so it will come out of integration ds will be equal to q1 by epsilon naught. So E into what will be integration ds? It will be 4 pi r square, because the Gaussian surface radius is r. So 4 pi r square is equal to q1 by epsilon naught. So what will be the electric field? 1 by 4 pi epsilon naught into q1 divided by r square. This is the electric field. Now the force experienced, what is the force experienced by the charge q2 which is kept on this Gaussian surface? So the force experienced by the charge q2 will be given by F is equal to q2 into E. So what is q2 will be there? What is the electric field here? 1 by 4 pi epsilon naught q1 by r square. So my F will be how much? 1 by 4 pi epsilon naught means k q1 q2 by r square. So this is nothing but your Coulomb's law. So this is how we can also derive Coulomb's law from Gauss law. Okay, so this is it for today's class. Please like the video, share the video, and any queries you can just mail me in the mail ID which is given below. Okay, thank you for your kind patience.